Good afternoon, everyone. It is my absolute pleasure to welcome you all here today for Astro-Talks 2025, proudly presented by the Astronomical Society of the University of Colombo. Astro-Talks strives to be a platform which makes learning about the wonder of the universe accessible to all, which is why we are so excited to also announce that today's lecture series will be also open to university students from across the country, and a live recording will also be available online. Today's lecture promises to be an exciting event where you all will be able to delve deep into the fantastic world of astronomy. Now, it is my absolute privilege and pleasure to introduce our guest speaker for today's event, Dr. Janaka Adassuriya. Currently serving as a senior lecturer at the Department of Physics in the University of Colombo, Dr. Janaka Adassuriya holds a PhD in Astronomy from the University of Colombo and is also the first Sri Lankan to hold a PhD in Astronomy. He is an expert in the fields of astroseismology, astronomy instrumentation, as well as the machine learning applications in astronomy. Without any further delay, I would like to warmly welcome him on stage. Sir, the stage is yours.
Very good afternoon to all of you. So thank you very much for inviting me for this special guest talk by the Astronomical Society, University of Colombo. I think we have enough audience here. So today I suppose that we talk about astrophysics, basically how we go into the research area in astronomy and what are the potential research we can carry out in here in Sri Lanka, and the current the condition exactly what's going on here in Colombo University in the astronomy and space science unit. So some of the research experience I would like to share with you, as well as some of the potential areas we can start in research. Also, I will discuss in my presentation. So first of all, I just want to clarify this topic, the observations and modeling. And so 2 and 4, actually once I put this topic, so first of all I saw that there's a 2 and 4. So then I connected it 2 and 4. So it is kind of like a process of backward and forward. Right? The word is like backward and forward, or maybe go from this point to the other and therefore there, other side. So it's like observation and modeling. So when we look at observation and modeling, so I hope that this context is actually common for all science fields, right? All the research areas, not in astronomy, but in other fields as well. But when we look at astronomy, it's completely depend on observations and modeling nowadays. But earlier, it was quite different because we didn't have enough facilities, technology, like computer power and all these things to have a modeling part. But nowadays, it's completely actually depend on modeling part. So now the astrophysics is slightly different when you look at today, because most of the astronomers are actually working on the modeling part. But earlier it was different, right? So therefore, I just put my topic like observations and modeling because I just wanted to show you how important the observations as well as modeling. But nowadays it's quite different. Most of the people are involved in modeling, right? But I will show you at the end of the presentation. I believe that you understand how important the observation as well. So therefore, I will go here and there, observations and the modeling, and I will show you some examples how we take the model, how we take the observations to model, and sometimes we take the modeling part first and then go for the observations, right? So, okay, let's go. As usual, now everybody is looking for like ideas nowadays, AI, yeah, right? So I thought maybe as usual as you do, I just also ask about ChatGPT and Google Gemini, the definition of the modern astronomy. What we can say, how we are going to define the modern astronomy. So this is the basically the idea given by the ChatGPT and Gemini. Usually the astronomy is actually like studying of stars, planets, moon, asteroids, like different objects, right? Modern astronomy is a branch of astronomy that uses the advanced scientific methods, technology, and theories you already know. But we can just take about the definition from the ChatGPT. Observational techniques. Nowadays, the observational techniques have completely changed and then get advanced and advanced every day by day. So that is a very important in modern astronomy, right? Astrophysics, observational techniques. Then theoretical models came on top of that, right? And then the technology driven, of course, it's technology driven every day, but it's mostly now depend on technology. And the other side, if you can say the Gemini definition of modern astrophysics, beyond the time, right, of course, precise measurements, that is very important. Now, what will happen, every day when you look at, right, what we are trying to do is, we want to make it more precise, more accurate, right? So we want to minimize the tolerance, the error, or maybe the deviation, so therefore the precise measurements we need. Because this is very important area where we wanted to get the sometimes a 100% accuracy. 100% accuracy. Why I am actually telling that? Now, if you look at some of the predictions, right? Now, for example, if you do a prediction of solar eclipse or maybe lunar eclipse, right? Nowadays, we can actually predict it up to 100%. With the location, with the time, right? Where we can see in the earth and what time we can see. Exactly when it actually reach or the cover the full moon or the cover the full disk of the sun can be actually predicted. So that is 100% accurate. Why? Because we want to maintain that high precision calculations. So that's very important. And so the big data comes to the picture now, right? Earlier it depends on here and there observations. Now I also experienced the difference in astronomy like 10 years back or maybe 20 years back with now. It's completely data driven, right? Why? Because of these space-based missions, dedicated missions. Earlier, I will show you. Earlier we had only maybe just a telescope, Earth-based telescopes, right? They are very important, but we have to wait so many days to get a data, right? And nowadays we don't have to worry about that. It's completely different. And there's no use of telescope. That is a sad part of the astronomy right now. Anyway, so it is data driven right now. The big data is available. None other than the other field, compared to the other fields, now here the data is very, the data amount of data is very high, right? So you can get more data in this field free of charge. Let's see how free of charge. So that is a data-driven subject as well as it is a very important field. That's why you can go for a machine learning, AI models, right? Deep learning, all these things actually combined in the astrophysics right now. Multi-messenger astronomy, of course, it is a multi-messenger. If you look at the field of astronomy and astrophysics, observations, we can divide it into observation, the data collection part, right? You can see the data collection, and then these different windows, we can go to optical, radio, X-ray, and all these windows to get the data. So it is completely depend on data because this is a remote sensing area. Remote sensing means we cannot actually go close to the star or maybe a planet and then do the measurements. It's a remote sensing area, completely depend on the remote sensing, right? So therefore, everything depends on the data, but we actually get it remotely, right? So therefore, it's very important. And of course, for the data collection, we use the ground-based telescopes, space-based telescopes, right? Those are, we already know that, right? And then the other part is now the modeling. So as my topic says that observations and modeling. So now we want to make a theoretical framework based on our to explain the observations. Sometimes we need models, as we discussed in other fields also, right? We have observations, but we need to find out what is the explanation for that, theoretical explanation. So theoretical framework is going on. And then we have simulate astrophysical system like stars, galaxies, right? Cosmological events like that. So then we have hypotheses and the predictions to test those the simulations or the models, right? And finally, basically we need analytical and numerical computations or solutions to get the model done. So these two areas are actually going on, right, parallel to each other, and then we go to and fro, right? So sometimes the observations we get, and then we need to make a theoretical model, theoretical framework on that. Sometimes, and very rarely, we get the theoretical model and then go for observation. That is also possible. In some cases, we need to prove theory, or maybe we need to make sure that the existing model is quite correct, then we need more observations. We have to go for more observation, and sometimes some actually astronomers ask, okay, this is the model, now we need this fine observation, like a very specific observations. So therefore we have to go to the other side. So it is going like a back and forth like that. So that's how the astronomy or astrophysics is going on. Let's see some examples, but before that, you already know the observational astronomy, how important is that and how important is that, right? People are always actually looking at the sky, right? And with the different instruments, they make it these are sextant kind of measure the angle and all, a small telescope, and they make some simple astronomical instruments as well. So this is how they develop the observational astronomy, because earlier we have seen that people involved in observational astronomy heavily, right? So they developed some ideas. So we have seen that there are some important eras in observational astronomy, Thales, Aristotle, Arcturus and Hipparchus, and these people actually just contributed in a different way, BC, right? So it is a very long time back. So this is how it came up. Now when you look at observational astrophysics, so these different areas are very important. If you look at the radio waves, right? The radio band, so we have a lot of facilities to observe the radio band. Now this is one example that Presidio telescope in Puerto Rico in Canary Island. So this is a huge radio telescope. Now it's already, this is no longer in operation, because a few years back actually this the focal plane, the focal point actually fallen onto the telescope, so the telescope actually get damaged. It's no longer in operation right now. Earlier this was the biggest one in radio astronomy. Now the Chinese telescope with a 500 meters, half kilometer, similar to that, is the biggest one in radio astronomy. And there are several other observation facilities coming up, like square kilometer array in large scale radio telescope project. So they are actually making very good observation right now. For example, this very large long-base interferometry is a radio telescope system, and the importance of the radio system is that we can actually combine two telescopes from two places, right? It is not like the optical astronomy. The radio astronomy has a facility or some advantage to combine two telescopes, right, in a different places. So then you can make a very big baseline, very long baseline, right? So let's say, for example, here one in this place, and there's another one in here. So huge amount of very long distance, like thousands of kilometers. So you can combine these two and then simultaneously looking at the same object at the same time, right? Then you want to synchronize these telescopes. And when you look at that, why you need that type of observation? You know that long baseline interferometry makes a high resolution images, very high resolution, right? So the resolution means, like, simply idea is that if you have the object. So if you know now, let's say there's two objects over here, but one object we can see as a one object. So if you want to see it as a two object, you have to resolve it. So therefore we need a huge resolving power. How do you get huge resolving power in this case? To keep this telescope away from each other very much, and then you can make a interferometry method. Usually this very long baseline interferometry method can go up to 90 microarc seconds. 90 microarc seconds. So you can imagine that. So that means the two objects, very close objects, right, separated by 90 microarc seconds, can be seen as a two objects. Right? So that type of resolution or separation you can achieve with this method. So that's very important. Now the observations actually now has actually come up with a very high standard, and the quality observations can be done, right? So these are some of the facilities right now we have. I mean, I just give some idea about how much is that 19 microarc seconds means. You can't even imagine that how much is 19 microarc seconds. It's very small. Now when you look at in the night sky, usually this is how you see the moon, right? The moon is usually like 29.43, like let's say 29 minutes. Then the sun is like also same as like 31 minutes. Venus, Jupiter, they can actually see in between this size of arc minutes, right? Jupiter. So you can imagine that they are arc minutes, not arc seconds, right? In sky. But you can go for 19 microarc seconds in that radio facility. So that is very high resolution. So when you look at the other areas like infrared, right, optical, ultraviolet, X-rays and gamma rays, data, electromagnetic window, you have different types of telescopes available right now for observation. They are in the know, so you already know. Do you know what about Gaia? What about that telescope? Gaia mission? You have any idea about what is Gaia? G-A-I-A, Gaia mission. Yeah, it is a European observatory. European Southern Observatory, European Union Observatory, dedicated mission to look at what? Basically the position of the stars, position and the movement of the stars, precise, right? So that is very important to measure the distance to the stars. If you have the correct position or the movement, the bubble motion and all these things in the star in the stars, so then only you can measure the distance to the star, right? Distance is a very important parameter in astronomy, astrophysics. It's a very difficult to determine, distance and the mass, right? So therefore, Gaia is a dedicated mission for astrometry. That means measuring about the proper position of the sky and the proper motion and how much they actually shifted, like kind of thing. So there are data. All these missions are give some data, so you can actually work it out. I'll come later on, right? So, like that X-ray, if you want to go for a data, then Chandra mission is there, Chandra X-ray observatory. Then the gamma rays, you can see Fermi, right, telescope. They are all of them are in operation right now. And then now the different areas came to a picture in observation astronomy. Like rather than looking at the electromagnetic spectrum, we also like interested on this looking at the neutrinos, particles, right? In solar processes, supernova, these processes always emit particles, so we are looking at the particles, we are detecting particles rather than just going for telescopes, particle detectors. Gravitational wave, right? It's a completely different window open to see the universe, especially with these facilities, LIGO and LIGO, and then cosmic ray measurements and kind of things. So it's completely different now. The observations came up to a different windows, right? So these are also relatively new in observation, but some of them are exactly producing data, right? So the type of observations, so when you look at the observations, you can actually divide it into several parts. Photometry, spectroscopy, direct imaging, particle detectors, as I earlier mentioned that, gravitational waves. So this is a new one, right? So it's going on still, but we don't get the data still, but it is relatively new area providing the data. For example, photometry and television, spectroscopy, there are a lot of other missions also. LAMOS is one dedicated mission going on in China, right? And this is a interesting one to particle detectors. It is a chemical detector in Japan, so it is filled with water, right, with the photomultiplier tubes to detect neutrinos, right? So underground neutrinos, like maybe 1 kilometer in deep, right, from the surface of the Earth. So that is a nice detector, basically detecting particles. So these are some observations we can see. I just wanted to show you my observational experience. I thought maybe it's interesting for you also. So my observational experience actually goes with the optical telescope basically. So this is where I worked during my PhD and all time. So it is a Mount Abu observatory 1.2 meter reflector telescope in 1,400 meters above altitude, sea level. So it is a nice telescope. You can observe infrared also because it has a liquid cooling, nitrogen cooling facility. And there's another one actually I use it like a half-meter telescope, remotely operated. So you don't have to worry about to go there, and then you can operate it from the university. So these are some of the telescopes I use it. And this is where I actually worked it before I joined University, Adassuriya Institute. So a half-meter telescope again with a CCD camera and the instruments. This is also another place I visited for observation in China, Wuhan observatory in China. So some of my experience. They are very interesting, right? Observational experience. I mean, so these days you don't get the observational experience very much because we are completely depending on the data, right? Data-driven research. But observational part is very interesting and very, important as well. To complete, to become an astronomer, right? I mean, you can't say astronomer without knowing about how to observe, right? So that's my definition. Okay, so this is again the same observation. Some facilities over there. Right. Now I will go to this the observation part, the photometric observation. What we can actually get it from these photometric observations. So the photometry, we measure the amount of light, right? So through media filter systems, in a different ways. Now earlier we actually used this photon counter to measure to do the photometry, to measure the amount of light. Photon counter, right? Now we don't actually use this because this is out of date now. So you simply use this telescope with a CCD camera, right? You can directly use the CCD camera. That's called CCD photometry. We don't go for a photon multiplier or photon counter. CC photometries now can actually provide all the data from photometry. Let's say now in photometry you measure the amount of light actually emitting from a star, right? Now this is a one light curve, right? That's showing like in the different figures DVR bands, right? D means like a blue and violet, visible and red, right? So these are close to those bands, like kind of a white band filters, right? So then we can observe the same star using photometry with the different bands. So you can see even how they differ, right? So now the B band actually just give a light curve. It is more, peak is more higher than the rate, right? So therefore you can see the same star actually respond to light, or maybe just observe it. The response is different in different bands. So you can actually study about these bands, or maybe just get this light curve first and then do the analysis. So this is the observation. So let's go for the observations further. Now for example, now this is our observation using that small telescope. But since you have this photometry mission like Kepler data, right? So the Kepler observed millions of stars right now. It's available, the light curves. So these light curves can actually give you no information. So I can't actually tell you all the information right now, but I will show you one research we can actually carry out. So this Kepler observed light curves of billions of stars. We don't know exactly what are these stars, right? They are maybe binary, they are maybe pulsating, right? So there are different types of stars. We don't know. So the light curves are available. So therefore when we take the light curve actually looks like this initially. You can see some variation. Basically they are variable stars, right? They are variable stars, but since we can see the variation, then what we can do is we can directly find out what are the frequencies or the variations available in this light curve. So then you can simply convert this light curve into a Fourier transformation, and then you can find out what are the available frequencies in this the star. So this is the Fourier power spectrum, right? So you can see the Fourier frequency available here, Fourier power spectrum, and then we show you the available frequencies in this star. Frequencies means variations, basically, right? Variations. Might be a binary or it might be a pulsation star. So we don't know exactly, but we can get this frequency, the available frequencies in this star. So similar to that, you can do a lot of stars and then get this Fourier spectrum. First of all, we determine what are the frequencies available, right? So then what we have to do is, right? So this variation actually comes from basically from interior of the star or maybe exterior, but I don't actually show you here the exterior like a binary eclipsing. So the binary eclipsing also actually just produce some variation, but basically this type of variation you observe in pulsation stars while they are actually vibrating, or the star actually vibrates or pulsate within its surface, right? The surface is actually pulsating or surface is varying, right? So one part is actually just expanding, the other part is contracting. So this is a kind of a very complex variation. So it can actually happen because of this. The sound waves, basically they are called acoustic waves. Because this is a gas ball and this is vacuum, that cannot come out, right? So they have to rebounce it inside, and they will make some standing wave patterns inside, right? Standing wave patterns. So then the standing wave patterns can be a different, right? Like a red one is one, and the green one is another standing wave, right? Blue one, like that. There are different number of standing wave options you can see inside. So because of that, what will happen, this the standing waves actually reflect how we actually get this, see that standing wave inside that. It will reflect through the surface as a variation, Doppler variation, right? So the Doppler variation will give you some differences, like one place is just expanding and the other one is contracting, or maybe just going towards you and going away from you, right? So that is a, so this reflection we can see as a variation here, right? The light variation or the amount of flux variation will be measured. So that's how the table actually observe it, and it's available. But before you go for this analysis, there are a lot of the corrections, right? The data processing has to be done. It's not a very simple case, right? You have to arrange the data before you do the analysis. So that part is very long even sometimes. So most of the missions, the advantage of that, most of the missions, they already done the basic reduction part or the correction parts. So the corrected flux is available right now. You don't have to worry about that also. So that is a bad side of the astronomy today. Because you don't know what are the corrections to do for these raw data. These are not raw data. These are process data. So you miss some parts, right? So therefore, this is already raw corrected data. Some of the things are corrected. Then only you can just go for this analysis and get the frequencies done. So basically, now this is an observation, right? This is an observation, and then we see some parts are actually vibrating, and we need some sort of a theoretical model for that, right? Theoretical model for that. Let's see. Now we observe it, and then we found out some set of frequencies, right? Set of frequencies. Some of them are harmonics, harmonic frequency, like 2, 3, 4 times of the first frequency, and some of them are not, right? So like that, there are huge frequency table you will get it in this observation. The thing is, how are we going to explain this, right? I mean, this harmonics, how this harmonics actually produce, and then non-harmonics like that. So then you need some sort of a theoretical understanding for that, to understand, to explain that. So we made some theory, okay? So of course we have theory right now. Now these are, kind of the displacement equations in 3D, right, in polar coordinates, and this is a spherical harmonic equation. So then what we can do? We can make a theoretical model, right? We can make a theoretical model. That means what you see through the Kepler telescope, there, so we can produce here, right? In computational way, using computational techniques. So we have theory, so we produce some models based on this, right? So these are kind of animations, right? Even this animation actually made out of that theoretical model, right? This animation, this can be animated nicely, right? So these are radial oscillations. That means usually the star actually vibrates radially symmetrically, or maybe this is radial and unradial both, because it is radially actually oscillating, as well as some of the parts of the star it has some sort of a local variations as well. So that is called non-radial variations, right? So this modeling can be done using theoretical explanations, right? So kind of like here, this is an non-radial oscillation. And for this, to model this one, you need the understanding, the theoretical understanding. So that is another part of astronomy right now. Okay, you have to make your own theoretical model to explain the observations. So that's that will come always with that. So when you look at in research, what we can see here. Now we have the power spectrum as what we see, the frequencies available, right? These are observations, the observational frequencies, the power spectrum, and then here using a different oscillation or theoretical modes, we can produce these frequencies. The available particular star, available frequencies, right? So that means theoretical model produce all the frequencies, right? Because that is the beauty of that having the theoretical model, because we have a lot of options, right, to reproduce it. So when you reproduce it, you can see how many frequencies are available. Now for a particular star, right, you just change the star like the properties like radius, the mass and all. So you have lot of frequencies available in this model. So these are P modes. P modes mean pressure modes. The available acoustic pressure mode, vibrations. That standing wave modes available. So that can be predicted like this, right? This is a one example that. So these are P modes and here G called gravity modes. But these are different types of modes. You can predict it, and then of course you can test this in that observation, right? So the frequencies from the model is now it's showing that okay, there are some frequencies available in this particular star. These are the observational power spectrum, right? Observational frequencies. So therefore we can match the observation with the theoretical model. What is the importance of matching it? Let's say you don't know the properties of the star. And the astronomy, we are always worried about these stellar properties, right? Stellar parameters. They are very, very difficult to determine. So therefore, if you know the stellar parameters accurately, then you can, one way is that you can test your model. One way is that you can test your model. Because theoretical model is not perfect at all. They are not perfect at all. They are different. I mean, there are a lot of deviations and there are a lot of limitations in the model. So how do you test your model? Then you need to go to the other way now, right? Once you make a model, then sometimes the astronomers ask, please do observations, more and more, and use my code or use my model and see whether, and just inform me what are the deviations, the limitations. So then only you can fine tune your model. So that way it is very important this go back and forth, right? Observations. However, now let's say your theoretical model is perfect, right? It's not perfect, right? But up to some certain level it is accurate enough. So let's say if you observe an unknown star with some sort of parameters, right? You don't know exactly, so you can determine the parameters. That's the point, right? With some accuracy. So therefore, we can just mention that. So in order to get these type of frequencies, right? So this particular star has a set of parameters, because in order to produce this frequency model or the table, you need to input a lot of data, right? You need to input a lot of data, like basically mass, radius, but that is not all the data, right? There are a lot of other features like hydrogen amount, helium amount, right? What is the size of the core, right, of the star? So when you just input all these things, that means you have some understanding what's going on in thermodynamics inside the star, right? So there are a lot of physics you might get involved in that. The other thing is, we are not really know about the physics what we learn here, whether they are exactly true in a very kind of a extreme environments. Extreme environment means inside a star is an extreme environment. Temperature 150 million Kelvin. Can't believe, right? We can't achieve it there. So we can't test. So therefore, one thing is that we can test whatever the theory we produce here, whatever the theoretical understanding, the laws, physical laws, whether they are exactly tallying with these extreme conditions. That is another important of doing this one. So when you look at these models, so therefore there are a lot of parameters you have to input it here to produce these models or the results. Therefore you can see whether they are maybe agreed or not. You can agree with the set of parameters or the set of theories. Right? So this is one example. And this is actually another example that because I faced this problem when I actually did my PhD, because now these are called evolution tracks, right? stellar evolution tracks. That means now let's say if you determine a star, right? If you observe a star, you don't know the star has a lifetime, like us, right? Early age, middle age, later, right? The final age, like a destination where it goes to end up with that. So then there's an evolution track for a star. So it is very important to know about, if you observe a star, where they actually locate in the evolution tracks. Whether they are in a very early stage or the middle stage or maybe later stage. So therefore, we just make again a theoretical model, right? We can produce a theoretical models for the evolution of a particular star using these codes called the MESA, right? This is a very sophisticated code at the moment available among the astronomers. So this code is actually just using it, and then you can actually just draw evolution tracks for different masses, 1.7, 1.8, 1.92, like that. That is the other thing, because we can plot any evolution track with any number of mass steps. Even 1.71 even you can produce it, right? 1.71, 1.72 steps, 0.01 mass steps. But we have to be careful about that, right? How we going to actually just make it. So therefore, it is very important. I think time is going up very quickly, right? I have a lot of things to discuss. So anyway, show you. Now these are some of the observations we place it, right? These are my observations, I place it. But still, I could not say that whether it is a 1.7, 1.8 or 1, because we are not really, but this one is slightly deviating. Of course, we can remove it. That means the star is not close to 1.7. But we don't know exactly 1.8, or some of the tracks are actually overlapping. Why? Because the other parameters, if you draw its evolution tracks, the other parameters like hydrogen amount, right? The helium amount, metallicity, then the other parameters, all these are actually dependent when you draw it. You don't know how it is. So you can imagine it is a parameter dependent model. Set of parameters at the same time. We can fix the set of parameters and we can change one. But then how we say that? You don't know, right? So therefore it is very difficult. Now here, we can say that sometimes when we have set of models, so we can get the best model by just calculating chi-square minimization. So we go for chi-square minimization, right? So this is maybe the mass exactly between 3.2 and 3, but this is not for this, not related for this one, right? So again, different star. So that kind of calculation or computation you can do. Now because of that problem, now if you have several parameters observed, right? Several parameter dependent, you can go for these corner plots. Corner plots means that now here, that star actually depends, the model depends on mass, metallicity and age. We don't know age of the star, right? So therefore, we can go for this type of technique called corner plots. So it shows that at the same time, all three parameters you can show at the same time using this plot. So therefore, you can actually get the optimum set of parameters, optimum set of common parameters, right, for this type of observation. So that is, I will go quickly. Now here in this case, in the previous case, if you want to actually calculate what will be the amplitude of this, that means the amplitude, the star actually vibrates with some sort of amplitudes, right? Let's say radial amplitude, how much actually it expanded. If you want to calculate that amplitude, then you have to go for a theoretical calculation. So that's what I mentioned here. The theoretical amplitudes you can calculate with the available theory, but you need a lot of other parameters to calculate to get the amplitudes. So however, then all these like the temperature, gravity, density, mass, and all these things you have to input to your model and then see whether you can carry with the observation. If not, redo the process. So that is how it goes. It is very, very time consuming, right? thing, like you have to, because your parameter set is very big, right? So you don't know how they actually change the different parameters. So this is kind of. So again, now this is how they plot it. Now these are theoretical curves of the amplitudes, theoretical lines, and the theoretical lines you have a lot of calculations. You can produce any theoretical line. Then you can place the observations on that and see how they approximate to the observations. Right? So we can get some conclusion based on that. So this is how it goes. And this is another modeling, right? Observation and modeling of a binary star. You already know the binary stars look like this. And the binary star light code, the observed light code is something look like this observation. Kepler, let's say Kepler. So you have a primary and then you have a secondary minima, the primary and secondary eclipses. So this is an observation. So then, that you can see here, of course you can actually model the binary using again the available codes. Right? I use actually several codes like WD code and again there are very good codes for binary modeling. So then I just use these models to produce these observed light code. You can see the observations, right? Nicely matched with the theoretical curve, but not nicely because you can see here the slight deviation of the red line is the observation and the dark one is the observation, red is the theoretical model. Still, you will get some deviation. This is the residual. It's not perfect, right? So therefore, it is not really easy to model it. So very difficult to get the perfect model. It depends on that. So that's how difficult, right? So yeah. So that's kind of. So when the spectroscopic observation, if you do, when there are several facilities to observe the spectra. This is a telescope and a spectrograph. So you need basically these two instruments to observe the spectra. Now these are some of the spectra. Then these are the observed spectra from our telescope, right? Let's say this is solar spectrum, Vega, Spica, Arcturus, right? Different type of stars. And this is you can see H alpha line, hydrogen alpha line, right? Very clear. But this one is emission line over here, right? These are absorption lines. We don't know why, right? So it is very questionable that why only the data split is actually the emission line. So that is a very interesting question. But all of them actually do observation. Now this is observation. So observations are like usually the spectrum that we see here. And there are different type of observatories actually produce different spectra. Mount Auburn, Ramos, the Market telescope. This is low resolution spectroscopy. You can see this is high resolution. How high the resolution, right? So you can see a lot of details available over here, right? So this is a Market telescope in Canaries Island, right? It is a very high altitude. You can see even the clouds are available above the clouds. Right? You can see the clouds below, right? So this is a Market telescope with this much of high resolution. Now there are a lot of steps actually we have to follow for preparing the data before we get the final results, right? Spectroscopic data, how do you prepare it? There are a lot of corrections, bias elimination, noise reduction, flat feeding, wavelength calibration, kind of everything we have to do for our data. That is the interesting, that is the important part, which I actually get some experience, right? But nowadays, since you have the data available for large, you don't have to go for this raw data process, right? Nothing to worry about this correction. But these corrections give you a very important information, knowledge, right? Why they do, how they do. It's very important to know about from scratch, from A to Z, right? So we visit, but anyway, this is very important. So there are a lot of corrections, but I will just make it very short, right? Because I think I have to also finish it 1 o'clock. Right? These are some noise reduction steps, like the dark current. These are some noises available in the instrument. CCD camera, it is an instrument, so it has a lot of noise, unwanted signals. We have to remove it. That is the most important part in data analysis, right? So when you remove that the dark part, so you can see how it comes like this only. This is before the dark correction, this is after the dark correction. Kind of, right? So then spectroscopy, you can do a lot of other things like stellar spectroscopy, can do temperature, composite surface gravity, like that. So these are observations when you made it. So these are observations. So then how do you produce it? Of course, you have to produce it theoretically. Spectrum, right? You have to produce theoretically. So you should know about the theory. That is the important of knowing physics. So how the line, hydrogen line actually comes, right? Hydrogen emission line, absorption line, how they produce in theoretical. So therefore, we need to go for theoretical modelings, and then so in order to, let's say, this is an unknown spectrum, we don't know any idea about the temperature, gravity, metallicity of the star, right? But we observe it. How do you get it? You have to model it again. So there are a lot of models available again, but you have to be very careful about that, some of the models. So this is what I use it here to produce the artificial or theoretical spectra or the synthetic spectra. So you can see here, the red line is the observed one, the black line is the star which I actually produce it with a temperature of 7300 K, gravity is 4, metallicity is 0, rotation. So you can put the rotation to the model, right? And then you can predict it, like if the star actually rotates with 30 kilometers per second, how the spectrum will get it? How does it look like? Right? So therefore we can vary. That is the advantage of having model. You have enough flexibility, right? You have enormous flexibility to change the parameters. So therefore we change it. Now this is changing from 7300K, 7500K, 7700K, like that. But still, I would not get the observation with the theoretical model, because you can see the dip here. Now the red one is here, the model one is actually the dip is known. So therefore, this is not perfectly modeled. You have to again and again redo the modeling and then get the perfect set of parameters, right? So therefore, we have to rewrite the parameter set of parameters and redo the model. So however, finally, you can actually reach up to a certain parameter set where you can actually satisfy. So this is again the same way, observation is made, there are a set of models. So here, this model is deviating, right, very much. Now even, you have to explain, that is the other thing, right? Why you can't get this with this set of parameters? You can't actually, why you can't actually get close to the red line with this set of parameters? Because you can't do like a blindly, right? Like a black box. And there's no way of doing that. Every day you have to change one by one. Then you need some understanding which parameter exactly trigger that drop, the width of the line. Maybe the temperature, maybe the gravity, maybe the metallicity. So that knowledge you should have, right? So therefore, you learn a lot of things when you redo it. So you should have some idea, then you can make it very quickly. You can come to some sort of a conclusion. Otherwise, you might actually end up with somewhere else, right? So these are some of the things. Okay, those are some of the things I showed you. The possible ways of modeling and then the observation, right? The possibility of going for modeling and the observations. So the both sides, right? So the modeling and the observation data are equally important, but nowadays people most of them are actually involved in modeling, because you need more models, right? More models. So the different set of parameters, different kind of limitations, right? Boundaries we need. So therefore, people involved in more modeling. So that means you need more computation, right? Knowledge, computational experience about that, theoretical knowledge, as well as modeling experience, right? Programming, everything. So that is now what you can see. So then the data availability I can show you here. The data is available everywhere. Free of charge, paper, tests, right? Then there are a lot of data sources. available. These are some of the things actually I use it usually in my research work. Basically, there are a lot of tools available, but the important thing is maybe if you can get some experience about writing a code, writing a model for a particular thing, at least maybe how a temperature or a spectral line profile, hydrogen alpha profile, how you can produce it theoretically. That may be a very good exercise for you, right? So that is observations available on to test those things. Okay, so that's basically I have it, but last two slides I went very quickly. So to complete it, we have to go to another meeting and complete the situations. So anyway, that's about what I have to tell you. So if you have any questions, we can discuss with a few minutes. Do you have any question?
Thank you, sir. Your expertise in this field is truly incredible, and I'm sure everyone here today learned a lot of new things about the field of astronomy. Now, I would like to invite the President of the Astronomical Society, Mr. Janaka Adassuriya, on stage to present our guest lecturer, Dr. Janaka Adassuriya, with a token of appreciation. Thank you, sir. Now, in order to conclude today's event, I would like to invite the Secretary of the Astronomical Society, Mr. Adassuriya, on stage to deliver the vote of thanks.
Good afternoon, everyone. Thank you, Dishaka. So, first and foremost, I would like to extend my sincere gratitude to Dr. Janaka Adassuriya. Despite his busy schedule, he agreed to participate as a guest lecturer for today's event. Next, I would like to express my sincere gratitude to the head of the Department of Physics, Senior Treasurer and Advisor of the Astronomical Society, Senior Professor Professor Chandana Jayaratna, for his continued support to the Astronomical Society. And of course, despite your busy schedules, I would like to thank everyone who attended today to make this event a success. Thank you.